as I mentioned, that is the title of my talk. So today, I will present a formal approach to verify PLC software correctness during evolutionary upgrade. Actually, it tackles a key challenges in industrial automation that ensures the upgrade don't break the previously corrected behavior. In today's talk, I will cover the motivation, our patronage-based containment framework, as well as the equivalence checking framework, symbolic equivalence checking algorithms, some experimental results on 80 real-world PLC programs, one industrial use case, and finally, open research direction. So first, the point term in my work I use that is a PLC. So what is PLC? So PLC stands for the programmable logic controller. So it is a small industrial computer used to control the machine autonomously. And PLC works like the brain of a machine. Just like our brain takes the decision, a PLC similarly decides what machine should do. And it takes the input from field, and the input signals are generally coming from the sensor, push button, switches, the temperature or the pressure device. It processes the input using a program. That means the inside PLC, the program logic is stored, and that says that is if this is happened, then do that, and it gives the output based on the logic. The output can be the motor off or motor on, or the lights on, light off, conveyor belt movement, valve opening, and so on. So, and one of the important points is that the PLC work continuously and very fast. So it checks the inputs and updates the output uh, many times per second. It's a cyclic time. And mainly this application is used in the factories and the industries like the manufacturing plants, power plants, water treatment. And as there is some PLC software is there, so if we can change the control logic, it's easy to change the operation. So if the process changes, we just change the program, not the right in the entire. In the PLC domain, there are more or less the four categories programs are there, which is called the IEC 61131, that is the international standard for the PLC programming. And there are the four kinds of thing. One is a ladder diagram. Some books it's called the ladder logic. Second is the functional block diagram, FBD. Third one is structured text, and fourth one is sequence function chart. So ladder diagram currently is not used in popular way, but remaining three remaining three languages are used. Functional block diagram is a modeling language. Structured text is a programming language, and the sequence function chart intermediate between the programming and modeling language. So it looks like that. So this is the ladder diagram, and uh, this is the ladder diagram. This is the functional block. This is the structured text, and this is text. So industrial systems, for example, the running assembly line or the robotics arm, they keep evolving. Uh, it might be add new sensors or the safety checks and updates. But every upgrade, there is a risk of breaking the earlier correct behavior. And that leads to the costly downtime or the safety issue. The traditional regression testing is manual and incomplete. That means there is a scope for bug. So if we ask a formal question, does the new PLC version preserve the all behaviors of the old one? If the answer is yes, we then we can candidly say that the upgrade can be certified with confidence. Now, uh, you might ask one question, that is, are not there is already tools and techniques available for the PLC verification? The answer is yes. In the safety critical PLC verification has grown significantly since 2000 and with extensive literatures on IEC 6113 compliance languages. But the most existing methods focus on the property verification, either the model checking or theory. The tools like verify apps that exist, but they assume the net structure is static, and they're struggling with the PLC tick semantic, that is the cycle-based synchronous execution. So there is a gap. So the behavioral verification also in the well studied at code and the model level, but focus on generally property shifting, not evolution. So there is a gap. There is no prior work on a path-based containment specifically for the PLC software output. And we developed this, we implemented this method and developed a tool called the ontology, and that is the unique selling point of our tools and techniques. So, to make the concept more concrete, let let us consider an automatic plant where the PLC controls a robotic assembly steps. So this is the original version. In the original versions, the automated robotic sum transformed the items from the conveyor belt A to the conveyor belt B. And the conveyor belt B, they uses a custom scaling sensor to verify the parameter whether it deposit to either the green bin or discarded to the waste bin. In the upgraded version, a safety guard sensor is added over here. And when the safety guard is placed, the robot proceeds with the item transfer and the scaling checks and compute the scaling factor adjustment parallelly for increased efficiency. So, in that case, if I can make it very simple way, that is in the original behavior, the logic is move on, detect object, grip and place. Whereas in the upgraded versions, a quality check condition is inserted before the grip. So, in that case, the classical tools like library testing block is not useful for the two reasons. One is the classical testing time for the SFC in the proper testing environment is a 3 to 5 minutes. It's a very simple thing. And second is the older version is purely sequential. What is the upgraded version? That is the concept of parallelism. As the custom scaling function is carried out parallelly. So, what is the solution? So, our solution, the key solution is a symbolic function. But the key idea is we have a SFC, and this SFC will be updated by some upgradation rules. And from this SFC, we need to construct a formal model. So actually, the input is to SFC, and there is a Petri-net model constructor, which converted the SFC into Petri-net model. Then we break the model into the set of paths by path constructor by introducing the cut point. And then there is a path-based equivalence checker, which checks the for all paths in the original, there exists an equivalent path in the upgrade. So if the one direction is satisfied, then you can tell one model is contained in hand. And for the non-equivalent path, this containment checker also gives the which path is non-equivalent. So here, so again, the main component.
Question.
Yes. Yes.
Yeah. So Deepak here. Yeah. So I think I've asked you this before, but I mean, in this example that you've given, the new system is not equivalent to the old. I mean, the new controller is not equivalent to the old one, right? It's doing something more. So how will you expect the two controllers to be equivalent, or is there some other notion of equivalence which I'm not?
No, here basically, you can say that whenever the upgraded takes place, it adds some behavior. So we are not checking that particular part. So that's why we are doing the one side. And here the notion of equivalence, we have modified it using some adding the two functions. One is the path extension, another is the path merging. Suppose in one version it's a very straightforward. In the other versions, we can check something. So there is a two branches there. So that will be taken care of. So in the original version, it's a two branch, and in the upgraded version, there is a some conditions, one path, and the negation of this condition is another part. In that case, basically, what we have to do is we have to do the path merging. So this and this will leads to the true. So using this manner, we are making the content.
Okay, maybe it will become clearer as you go ahead.
Can you please repeat?
No, I think you go ahead. Maybe it will become clearer as you present. Yeah.
Yes. Yes, I have one example. So through this example,
okay.
So here, so three main components. One is a Petri-net model constructor, another is a model analyzer, and finally is a report generator. So now, first is the model constructor, which takes the SFC like this, and it converted to the Petri-net model, and you can see this is the one-to-one correspondence. Every steps corresponds with the places. Every transitions are correspondence with the transitions, and the actions associated with the steps will be treated as a sequence of function associated with the places. So this is the fun F2 F3 kind of that. So now this is the main slide. That is the concept of execution cut point, which will be useful for our containment chain. So here, first we try to understand what is the containment means over here. So here, so every computation in the original PLC program, a correspondence or equivalent computation must exist in the updated version. And if that is guaranteed, then the upgrade is correct with respect to the previous behavior. So note that we are not doing the full equivalence checking here. So we are doing the containment, that is the one side. And it is important because updates often add behavior, which is absolutely fine. as long as they don't move the old computation space. And due to presence of the loop, suppose in this model, uh, in how many times loop will be executed, we do not know, and because we are taking the symbolic here. So for this purpose, we introduce the notion of the cut point. That is, we introduce the cut points that place containing the value. So in this figure, the place P1, P7 are the place containing the values as a cut point, and the place P10 is also marked as a static cut point because it's a three places of the synchronized conditions. So it's treated as an output of the PLC program. And the P1, of course, there is an initial mark. So initial markers also the cut point. Now, if we can construct the paths from the cut point to cut point without having any intermediary cut point, then the red color dotted boundaries are the path. So in that case, we can't establish that any computations can be represented as a concatenation of parallel. So for this purpose, because this path and partially the path alpha 2 is partially parallel with the path alpha 1. So for this purpose, if we place some mark some places as a execution cut point, for example, the P6, P8, P9, and P11, then we get the green dotted boundaries as a path. That is alpha 1 prime, alpha 2 prime, alpha 3 prime. So in that case, we have to find out that is we can capture any computation in terms of the parallel. But now question is that how we can identify this green colored dot as a path. So the tricks is there that for all enabled transitions are fired simultaneously. And on firing simultaneous firing of the transitions, when it goes to the new set of marking, if any places on this set is marked as a cut point, so mark all places as a execution path. And for this purpose, it reduced the state explosion and preserve the PLC tick semantics and improve the symbolic equivalence precision. So let's take this example here. It's a custom scaling functions over here. So this is the single loop, and we just this is the source SFC, and here we just parallelize these two loops, and this is the upgraded SFC, and this is this spectrinate corresponds to this SFC, and this spectrinate corresponds to this SFC. And this dotted boundaries are the path for this figure and this figure. And find out that is the alpha 1 is equivalent to both the beta 1 and the beta 2. Alpha 3 is equivalent to beta 7. And the alpha 2 is equivalent to beta m, and beta m is of the form that is the beta 3 concatenated with beta 4 and the beta 5 concatenated with beta 6, that will be merged. So this boundaries as as a merged path, which is equivalent to the alpha. Similarly, for the our motivating examples, so this is the SFC for this original systems, and this is the SFC for the upgraded system. So blue color indicates that upgradation takes place. And this is the original Petrinate model from the original SFC. This is the upgraded Petrinate model from the upgraded SFC. And this is the result. So here the alpha 1 is equivalent to both the beta 1 and beta 2, beta 1 dot beta. Sorry, it's an extension, and so on. So here both the path merging and path extension takes place. So we have also run our experimentation on the 80 the PLC applications from the OSCAT library. And depending upon the lines of code and the structure and how the how many loops are there, or what level listings are there. So we categorize between basic, simple, medium, and complex. And we also inject some manual error, and our verifier can successfully and detect the faulty output. So observations over here, we also compare our tools with the verify apps, and here we find out that the content checking time is not more preferred to verify apps, because for the verify apps they first they set key to ST0 from, then the ST0 to SMB, and then they use the UX SMB. So model construction time is finished. So that's why. So major limitations of that, it cannot handle the hierarchical SFC, so that extension is required. And non-bisimilar code it cannot handle, as well as it cannot handle the beyond kind of timing. So in conclusion, for this the SFC to upgrade, we can along with the PLC upgrade verification, you can say that this is the first industry level containment checker, and this is purposefully built for the PLC upgrade verification. So we believe these tools for the Ansharbhukti opens a new direction in the evolutionary cover formal verification, where upgrades are analyzed not as an isolated program, but as a behaviorally related families of model. So now, the final part of my talk is basically one the industrial use case, but the upgradation is also done, but in terms of the software migration. What the migration means, basically, uh, uh, mm, means it's a transforming the legacy code to the modernized platform. It's one way, it's called the software sustainability. That means you need to retain the customer, but the old systems are there. Now the customer need to migrate into the newer platform. And why? Because it's a it's minimized the operational risks. It's improves the security, regulatory compliance, etc. As well as the carbon emissions. So the overall broad problem is that from the heritage code uh, uh, to modernized platform, the code is migrated. But the major question is that whether these two codes are the behaviorally equivalent or not, although they have a different semantics. So here the benefit of this, what if we can do this verification, impose the verification problem in the software pipeline. So here the benefit is that we have to retain the customer using the certification. So the verification here acts as a certification. And the testing time is also reduced. So this is the this slide. So through these slides, I will illustrate the complete migration journey. That is how the third-party control systems can be transitioned into some modern IEC 61131 ecosystem with significant cost and efforts. So it starts from the legacy systems such as different automation in industry have their different proprietary language. For example, the Mod 5, Mod 3 CCF, Honeywell TDC, Emerson, Delta V, Mod 300 TCL. So these are all the different the proprietary language for the legacy platform. So now, but this programming language, this control language is hard to maintain, hard to visualize, and error prone during the update. So the question is that if we migrated to the ISA 61131 platform, or for example, SFC, it is a well-structured and graphical model, and that makes the system behavior easier to understand, verify, and modify. So migrating from the TCAL to, suppose here, the heritage language to SFC uh, mm, gives the industry better clarity, safer upgrade, and improved long-term maintenance. And it also helps the engineers to see the control flow clearly and reduces the misinterpretation and suppose advanced analysis too. So in short, I can tell that is this migration is not just a format change. It's a step towards more reliable, transparent, and the future-ready automation system. So here, what exactly they're doing? They are the third-party systems. They just extract the legacy specification in the reverse engineering, and then from the legacy specification, they try to map to the IA company functional specifications, or some open source, the open PLC functional specification, and then do the forward. So here, uh, when this to this happen in the design engineering phase, there is a scope of the verification is there. So our verification is basically our verification framework. So this is the pipeline that ensures that migrated SFC preserve the original TCL behavior. And for this purpose, we converted the TCL to PN and the SFC to PN, and then they use the path constructor and the equivalence checker. And in the equivalence checker here, the fix is that for each path in the TCL, there exists an equivalent path in SFC and vice versa. So we have to interchange this now. And it gives the equivalent set of paths to the non-equivalent set of paths. So let's take a toy example. So this is a conveyor belt, and there is a hyperspectral camera. Woods are coming, and it takes whether this is good quality or the bad quality. So this is the TCL code, and this is the migrated SFC code. So using the model constructor, we can make this Petrinet model, and using our previous tool, we use the model constructor of this previous tool of the Antarbhuti and get the Petrinet model. And this to Petrinet model is almost structurally similar. Of course, the behavior is equivalent. And if it gives the yes answer, it's fine. If it gives the no answer, that means we can't say. So the method is sound, but not complete. So it's a real life example. This is small TCL code snippet, and this is the Petrinet model. And basically, this is a place and pick systems from the conveyor belt to goes to the conveyor belt, and then do the custom scaling function. And this is carried out sequentially. In SFC, this is the migrated code, and here some parallelism is there. Now we break the model into the set of parts, but here the question is that sorry, this is the TCL code, and this is the corresponding Petrinet model. This is the SFC, this is the corresponding Petrinet model. But here we have to show that is any computation can be represented as a concatenation of the path semantically. How we can do it? So let's take on one example, and let's take the computation of the code P23. Suppose T31, 33, 34, 35, this is the end times, then the 36, then the 37. And the paths, the dotted boundaries alpha 0, alpha 1, alpha 2, and the alpha 3. So now, here we check that the new P23R is an empty. And the last member of the mu P23 is 337. And 337 is the last member of the part alpha 2. So the all members of the alpha 2 will be deleted from the mu P23, so that T37 and the T36 will be deleted, and alpha 2 will be put into the mu 23 PR. And then the last member is a T35 and the T34. So the alpha 1 is append before alpha 2 and so on. So this method is terminate when the mu P23 will be the end. So here the proof sketch is that first we have to do the construction phase from the mu P to the mu PR. Then by notion of path equivalence from the mu PR, we can do construct the mu P prime mark. But the P and P prime are the correspondence, of course. Without correspondence, we cannot establish equivalent. And then from the mu P prime mark to the mu P prime, again the reverse construction phase. And finally, we have to prove that is the mu P prime is a computation. That is, it satisfies the all definition and clauses of a computation. So finally, in this, this is my, again, this is the original TCO code. This is the corresponding PECTINET model. This is the migrated SFC, and this is the corresponding PECTINET model. And the blue color box indicate that that is the equivalent. So we can use the tools Antarbhukti for this new one, because Antarbhukti doing the containment check. If we can run this Antarbhukti twice times and interchange the input instead of the SFC, if we can do the TCL and using the press gen, we convert it to the PECTINET and then feed into the Antarbhukti. And SFC also takes on SFC. Then we can build the equivalence checker for the software migration use case. So again, we also experiment our this method with several real-life benchmark, and in the 60 to 70% cases, the business team report that the testing for production takes place, and the migration assistance will also help with this one, and it can the capabilities of this method, the data type migration, uniform, non-uniform, code motion, reading migration, code motion across groups. So this can be handled. So this is the demo of Antarbhukti, but I would like to show a demo of the entire the software engineering tools. So where suppose the upgradation is carried out with the LLM. So previously it is carried out by the human being. So if it is carried out by the LLM, then how the Antarbhukti will be taken care of. So this what my the screen is visible. This hello.
Yes, it is.
That is some software tool is visible in the.
Yes, it is. LLM.
Oh, fine. So it is called the ILMA, that is the LLM access software architect. So here there is a dashboard is there. Here the executive summary. Here we can upgrade SFC generator. Suppose we have already some example. For example, the elevator controller SFC, and I want to add some safety features. I can add also the reliability features. Under this reliability feature, these are the I can choose the safety features where the input safety validation is there. And here that all safety reliability access tactics, the software engineering tactics. So here that is the when and the what actions we need to do. So, and if I can click on the generate prompt and code for the upgraded code for this upgraded code for this SFC, it generates the full prompt generation. You can download it, and this is the original SFC. And this is the upgraded SFC. I'll just download this upgraded SFC. And then I go to the workstations where the Antarbook key is added over here. So uh, then I add two things. One is original SFC, another is upgraded SFC, and now I run the batch mode. So I'm just using the GPT-4. We can select the model Lama platform complexity. Yes. So now the verification is successful. Here, if we can go to the report generator, we have seen that is in the after the two iteration, this upgradation is correctly verified. So if you can see in the first iteration, it's failed because this is the original and this is the translated, and here this parts, these two parts, there is no part in the other portion. So this is ultimately just failed. So now, if we can go to after one iteration GPT-4, you can see that is the all parts are given. So one model is contains as. So using this manner, we use this our developed tool for the hallucination detections, as well as this LLM generated output verification problem. So this pipeline also very interesting for the hallucination. So thank you.